We can start? Okay. So, good evening, everybody. I will repeat a little bit what I did yesterday towards the end. So we distinguished the Monge problem which is a minimizing of this integral over all mapping T, which push measure mu to measure nu, and mu and nu are both probability measure. Let's assume that this is the same space. In general, it can be different spaces. Mu can live in one space and nu in other space. But let's assume that they both in a probability space on a domain of omega. And the Kantorovich problem minimize the double integral of C, X, Y, d gamma over all gamma in a set which we call pi mu nu is a set of all probability measure in omega cross omega, such that this marginal mu and first marginal is mu and the second marginal is nu. So and what we want to claim here is that we don't know if a minimum exists here, and we even didn't discuss this case. So let's put an infimum instead of minimum. And at this, we wanted to show that these two are equal. The two infima are equal, even though this is live in a space which is much more bigger than this space. Yeah. Remember that we argued that for any P which in this class, we can consider it as we can define gamma T in pi such that gamma T is equal to the push of the mapping I P of mu. By definition of the push forward of this is a function acting from omega to omega cos omega, and it push mu to this measure. In other words, this measure gamma is supported on the graph of T. So why these two infima are the same? What we proved is actually the fact the result that we get is that the set of all measure which are induced by mapping T is dense. Is a weak star dense in this in the set phi. But in order to obtain the quality of these two, we have to make some other assumption, because we need the compactness, right? And so we need to show that if we have a a sequence gamma n which converges to gamma, then this will converge. And this is true if the domain omega is compact and C is continuous. Yeah, because then, or at least in C0, because then we have the duality of measure with respect to the space. So let us see. Let us discuss a little bit the minimizer of the Kantorovich problem. So, like I said now, the existence of minimizer are guaranteed if C is continuous and X and Y may be different space, but compact. We can extend it to lower semi-continuous function C. Why is that? Because what is a lower semi-continuous function? It's a pointwise limit of increasing sequence of continuous function. That's characterized lower semi-continuous. So, so if we consider a function f a lower semi-continuous function, then the induced functional mu defined by the integral of f mu is also lower semi-continuous on Borel measures by this reason, right? Because it is a limit of continuous functional if we approximate f, if we consider f as a limit of increasing continuous functions. So so lower semi-continuity is enough to prove existence of minimizer, right? That's what we need. If you have lower semi-continuity if it's functional, then we guarantee to have a minimizer. What about space which are not compact? Polish space. Well, we define Polish space. These are the space which are separable and complete metric space is separable, like Rn, for example. It's again okay because in fact this set pi, so set of measure is tight. Well, it's because it has two marginals which are probability measure. If you take a compact set K in space X such that the measure mu n nu on its complement is smaller than epsilon, then for any gamma in pi mu nu, we can calculate gamma in the complement of this set by calculating it on X times the complement of K and complement of K times X and the complement of K times complement of K, which is smaller than 2 nu plus 2 mu. So it's actually 4 epsilon should be, 2 epsilon, right? 2 epsilon. So, so we have the tightness. And so once we have tightness, we have a narrow convergence. All what we need is to assume that C is continuous and bounded in sim B. So C, the cost function C should be bounded and continuous. In general, however, we are interested in cases which this is not the case. Two classical examples that are very common in the application is the quadratic or the norm case. In the quadratic case, we have to put a limitation we should see it later, we need mu and nu to be in the space P2, and in general Pk or Pq is the set of all probability measure Pq of Rn. Is the set of all probability measure mu, which has a finite q moment, so integral of x to the q. The mu is finite. So they have a finite q moment, and so we need to set some limitation in order to get the existence of minimizer for the Kantorovich problem. There is an interesting remark that we can note here, because we can replace x minus y squared by cxy. Why? Because just open the quadratic form, and you have x squared plus y squared minus x dot y, and the x squared, and if we integrate x squared or y squared the gamma, this is just doesn't depend on the measure itself, right? Integral x squared the gamma, by definition, is just the integral of x squared the mu, and the same for y, because of this definition of pi. So in fact, the only difference is that now, instead of minimizing the x minus y squared, we maximize xy, because we minimize minus xy, right? And this is just the interpretation of this is just finding a distribution gamma, which maximize the correlation between two random variables, which distribution fx and fy, mu and nu, right? You can see it's just a definition, and it shows why one of the reasons why this is interesting, this particular cost function. Another very interesting cost function is the norm. It's more problematic because, in general, there is no unique minimizer. We will talk about it a little bit later. We can imagine that what is the bookshelf shift that I mentioned here? So imagine that we have a bookshelf, and we want to move all the books one book to the right. So we can move each book one book to the right, or we can take the first book and put it at the end. So this is two mapping, which take the shelf and move it one book to the right. But the costs are equal. You can see that the cost of these two transport are equal with respect to the distance. Okay? Because we move n times 1 over n is the same as moving 1 times 1, right? Okay. Okay, now let's see what we can say about the Monge problem. So our goal is now to look for conditions for the existence of a minimizer for the Monge problem. The special, so meaning that a special case where the Kantorovich minimum is obtained at a measure which is given by, induced by mapping T. Here is the idea. We define a set of continuous function on the space X and on the space Y, phi on C continuous on X, psi continuous on Y. The sum of phi X plus psi Y is smaller or equal to Cxy. Then we can see immediately this inequality. This expression, the integral phi d mu plus psi d nu, is always smaller or equal than the integral of C d gamma, right? Because where gamma is in space pi. And this is because the integral of phi d mu is exactly like the integral of phi d gamma. And also psi d nu is exactly integral to psi d gamma on the space X times Y. So, and this inequality implies that you always have induce this inequality. So if we want to, so the idea is that we want to maximize the right-hand side, find such pair phi and psi, which will maximize the right-hand side, and hope that this maximum will be equal to the infimum of the right-hand side. If this is true, then we can hope to construct something from the maximizing pair phi psi and see and say something about the form of the minimizer plane gamma. What you can observe is that if phi is given, then we can take psi to be the infimum over Cxy minus phi x over all x. Why is that? Because psi is always bigger equal than Cxy minus phi z, right? Because of this definition. Psi of y is always bigger equal than C minus phi. So we want to make it a small, this is true for any x. So we want to make it as large as possible. So the largest possible psi will be this. This will cannot have something bigger than this infimum, which satisfies this for any x. So we so in order to increase the left side, we will define, we will replace, and we know phi, we will define psi to be this function, and it's called the C transform. The C transform of the function phi is defined in this way. And this will remind us some Legendre transform. We will see soon that is really a generalization of Legendre transform. So, and analogously, we can, if we know phi, we can define psi. Excuse me, if we know psi, we can define phi as the infimum of over y of Cxy minus phi y. Any function like this is called C concave, and we can see that if we replace psi by the C transform of psi, we increase this integral, and if we continue to replace now phi by the C transform of phi c, C bar transform of phi c, then we increase it further. So, in general, we can say, well, we can replace this by defining this term only on function phi, which and replace phi by the C transform of phi, and restrict ourselves to all functions of this type, which is called C concave. Let me show you some connection with subgradient of convex function. So let me remind you, C is convex, or phi C concave. So what does it mean? If f is a convex function, we can define the Legendre transform, which is always also a convex function, right, by this. We take the supremum of p dot x minus fx. P is a variable in the dual space of x. In the case for Rn, for example, P is just inherent. And the C transform that we just defined is defined by the infimum of over C xy minus phi x, right? So you see the connection, because if C is just minus x dot y, this is just minus the Legendre transform. Or, excuse me, plus x plus y, this is just the Legendre transform. We know that the Legendre transform is smaller, of f is smaller or equal to f. And if f is Laurent semi-continuous, then we have equality. Of course, if f is convex and Laurent semi-continuous, the double Legendre transform recover the function itself. We can prove the same thing for the C transform. If we take twice C transform, we get inequality. We can compare it to always smaller or equal than the function, the original function phi. And there is equality if phi is Laurent semi-continuous. All this can be followed from just from the definition. The notion of subgradient of a convex function is also well known. This is all the P in the dual space such to satisfy this inequality for any y. Fy minus fx is bigger or equal than P acting on y minus x. This is equivalent to all the P for which the fx plus f star P are equal, or where this for any x which realize this supremum, right? So this is by definition the subgradient of a convex function at the point x. We can also define the C subgradient of phi in equivalent way, in this way. So this is for hx, we define the C subgradient as all point y for which there is equality. Phi plus the C transform of phi at y equals Cxy. There is another notion, maximal monotone. Maximal monotone set is a set of pairs x, px, which satisfy this inequality. If you apply px minus py dot with y minus x, we get something, we get non-negative. And this will be true for any p in the subgradient of f, and px in the subgradient of f, and py in the subgradient of y. This is true for any convex function f, but if we have a set x px which satisfy this monotonicity property, it doesn't guarantee that this is a gradient, subgradient of a convex function. In general, there are examples that, for example, we can think about mapping from the plane x, y, or x, x1, x2 to minus x2, x1, or one, we'll call it p. Okay, so if we so if we take no, that's not what I want to do. Think about rotation in the plane of 90 degrees. Right? If we take point x1, x2 and rotate it by 90 degrees, get minus x2, x1, the inner product will be 0, but there is no, the graph of x1 minus x2 is not a graph of any convex function, of course. However, okay. When we know that the differentiability of f at a point x is equivalent to the fact that the subgradient is singleton, is composed of only one point. And also, if the subgradient, subgradient of sub C gradient of phi is a single if C is differentiable, and if C is differentiable at the point xy, then the phi is differentiable at x, and the gradient of phi is just the gradient of respect to y, the second variable of C at the point x and its subgradient. Rockefeller theorem. So this is the extension of the maximum monotonicity. We define a cyclical monotone set in this way, on the set xp. So for any sequence of xi pi, this sum of pi dot xi is always bigger or equal than pi xi plus 1. So we shift the xi to the right, say, and of course we consider xk plus 1 to be x1 to close this. So, any set which satisfies this property for any finite collection of points is contained in a subgradient of a convex function. This is this theorem generalize make a sufficient and necessary condition for a set to be a subgradient of a convex function. This is a generalization of the maximum monotonicity that we saw before, because the maximum monotonicity concerned only sum of two terms, and here we need it for any k. And the equivalent for C maximal monotone set, which we define here, is a set of all point x, y such that for any finite collection xi, yi, the sum of ci, xi, yi is bigger than the sum of cxi, yi plus 1. If this inequality is satisfied for any finite set in the multiplication space x times y, then we say that this set is a C cyclically monotone, and it always contains a graph of a subgradient of a secant function. This is a theorem that we actually proved. We proved it yesterday when we talked about when we defined the condition of stable partition, right? We did it for the special case where the space X is in general and the space Y is finite, but the same proof apply here. Okay. Let us see some examples. So the first, the case of X minus Y, the case of C is just the norm X minus Y. The C transform is the infimum of X minus Y minus V of Y. What does it? It implies that the C transform of V is one Lifshitz, right? Because all these functions, X minus Y is of course one Lifshitz in X. And the infimum of functions which are one Lifshitz in X is also one Lifshitz in X. At most one Lifshitz in X, right? So, so by devolution we see that in fact if the function V is also one Lifshitz, then its C-convex is minus V, right? So in particular, we have for any one Lifshitz function, we have this identity, right? Which you can see immediately why it's true. If Y is one Lifshitz, the infimum can be obtained at Y equal X. So this really gives us the duality of this case, very special case where all secant K functions are just functions of Lifshitz 1. In this case, X minus Y squared over 2, if we take the C transform of this, we can write it like Y squared minus over 2 minus the supremum of this, and this is just a general transform of this function. So the phi c is defined in this way. Phi c, if we take X squared over 2 minus phi, the C transform of phi is just a general transform of X squared over 2 minus phi. So you see the connection between the general transformers. And of course, if we define C to be just X dot Y, we get precisely the general transform. So this is really a special case of. So what can we say about existence of a maximizer to this problem? We said we want to maximize the left-hand side and see if we can meet the right-hand side. Do we have a maximizer? Okay, so let's see. Condition that we have a maximizer. On compact spaces and continuous C, we use Arcela-Ascoli and to prove that the set of functions phi psi or phi or the phi and its C transform is uniformly continuous, because if C is continuous on a compact set, it's uniformly continuous, and therefore, by definition, its C transform is also uniformly continuous by its definition. It's the minimum of a function which are, again, uniformly continuous. So we have equicontinuity on a compact set, and we can obtain the existence of a maximizer. So we still don't, so we know there is a maximizer. We still don't know if this is equal to the minimum. We know, we just know the inequality, but we still don't know if there is a minimum, if it meets the minimum of C overall measure in pi. But here is the what we actually proved. An optimal map for a continuous C, or this function C, is always supported in a C cyclical monotone set. Again, this is what we proved in a semi-discrete case. Let me see. So this is the theorem. If gamma in this is a C cyclical monotone set, and C doesn't have to be continuous, just finite function, doesn't have to be continuous even. Then there exists a C concave function phi, which meets this equality at any pair of points xy in gamma. Again, in the semi-discrete case, we call the phi C. We call it pi. The price is pi for the index for the point I, and the phi x is just the maximum overall theta I x minus pi. That's what we defined in the semi-discrete case, and the same proof we gave. If C happens to be continuous and the set gamma is compact, then we can also argue that these functions are both continuous. In general, we don't know it if C is not continuous. So here's the corollary. If you take any measure which is supported in a C cyclical monotone set for C bounded and continuous, it is necessarily an optimal Kantorovich with respect to this cost C between its two marginals. And here's the immediate proof. If we take a measure gamma, some measure gamma, and integrate it with respect to C on x dot y, because gamma is supported on a C cyclical monotone set, we can replace C by phi x plus phi C y, because that's precisely what we know, that the theorem tells us that there is such a function which meets this equality to C on gamma. And this is, by definition, the integral of phi over the first marginal of gamma and the integral of phi C on the second marginal of gamma. And then we can, and if we take any gamma tilde in the space pi with these marginals, it will be bigger or equal to this integral, because for any other point, phi x plus cy is less equal than C. Okay, so we prove that gamma must be minimizer. It's smaller than any other measure in pi. So in particular, if we have a set, C cyclical monotone set, and any measure supported in this, and we multiply it by any non-negative measurable function and consider the measure H gamma, it's also the optimal solution of the Kantorovich problem with mu H nu H, where these are the marginal of H gamma. Okay? Any questions so far? Everything clear? So here is a proposition, is a corollary for this. We have a weak continuity, weak star continuity of the Kantorovich functional. If you have a sequence mu n and nu n which converge weakly to mu n nu, and consider the optimal solution, Kantorovich solution gamma n, then there exists a subsequence which is converged to also weakly to a measure which is C optimal with respect to mu nu. How we get it? So we know that gamma n must be supported on a C cyclical Hamiltonian set which I call capital gamma n. So Black-Scholes theorem tells us that there exists a subsequence which converges to set gamma in Hausdorff metric. Let me remind you what Hausdorff metric is. One way to define Hausdorff metric is to take the L infinity norm of the difference between the distance function d from A and d from B. D from a set A, just the infimum from a point here, d of x and A, just the infimum over y in A of x minus y. So this is one of the definition, equivalent definition of Hausdorff, and we know that in a compact set, the all compact subset of a compact space are compact with respect to the Hausdorff metric. So since it is converging in the Hausdorff metric, the limit is also cyclical monotone. And the weak limit of the weak star limit of gamma n, which is gamma, must be contained in the support. But that's also a result that we know that if we have a weak convergence of measures, then the support of the limit is contained in the limit of the support of the sequence. So we obtain that gamma, the limit is optimal because it is supported in a C cyclical monotone set, right? Let me stress this one point so you can appreciate the power of this theorem and the meaning of cyclically monotone. So suppose we have the set x times y, and we pick up a finite set points. So let's call the coordinate x1, y1, x2, y2, and so on. And what does it mean that these points are in a cyclically monotone set? It means that if we assign x1 to y1, x2 to y2, and so on, and we calculate the sum of C, the cost of transport from xi to yi, this will be the minimum. This will be the minimum of all other possible matching between them. This will be the minimum over all permutation of C of some C xi y phi I. So this is precisely what we consider in the case of marriage problem, right? Only in this case we minimize and not maximize, but essentially the same, right? For any finite number of points, the matching between the first coordinate to the second coordinate in the set is the optimal one with respect to C. So in order, what this theorem tells us is that in order to make sure that a measure gamma is optimal for the Kantorovich problem, all we have to see is that just to check its optimality on a finite set. In general, we should think maybe if we want to check optimality, we have to perturb gamma with any perturbation, perturbation by sign measure which preserve gamma in the set to check if this is an infimum. But in fact, theorem tells us it's enough to do it only for sets of finite cardinality of points. This is quite surprising, actually, if you think about it. Anyway, so we want to, so far we know, at least in the compact and continuous case, there exists a maximizer of the dual problem, which is a pair of C transform functions. And we want to see what we can study from here about the existence of a solution for the Monge problem. So let us recall Rademacher theorem. Lifshitz functions are differentiable almost everywhere. So if C is locally Lifshitz, the second point, if C is locally Lifshitz, so are the potentials, because again, by this definition, it's an infimum of Lifshitz function are Lifshitz. And if mu is absolutely continuous with respect to the bag, then phi is differentiable mu almost everywhere. That's the conclusion from Rademacher theorem and the Lifshitz continuity of phi. That means that if we demand a twist condition, what is a twist condition? Look at the function from y to the gradient of C with respect to the first variable x. If this function is injective for any x as a function of y, for any x or for almost any x, then we call it such a C satisfying the twist condition. If C satisfies this twist condition, then we can actually differentiate to calculate the dual C dual psi. We minimize C over because here I have to put not x but z. C zy minus 3z. The minimum is obtained at z equal x, which means that if everything is differentiable at x, that means that the gradient of phi at x is just the gradient with respect to x of C at xy. So in particular, if C happens to be of this form, So H is strictly convex function, and it is homogeneous in this way, function of x minus y. If H is strictly convex and differentiable, then phi, then y is obtained by by this form. You substitute this H for C, and you get this expression. You invert the gradient of H. We can do it because H is convex, and then we get that y is just x minus some function of x, which is obtained by the inverse gradient of H acting on the gradient of phi. So there is a direct connection between the y, the point that is assigned to x, with the gradient of phi at the point x. Okay? So if we know that the quality exists between the dual problem and the direct problem, so there's no duality gap, then we know that this T must be an optimal solution for the Monge problem, right? And the twist condition guarantees to us that any solution of the Kantorovich problem is obtained by a measure which is supported on the graph of a function T like this, defined like this. This immediately gives us uniqueness. Why uniqueness? Maybe there is more than one solution for the dual problem. Maybe there are two functions, phi1, phi2, which satisfies. But if all optimal solutions are reduced by such T, then if there is more than one, we can take the average of these two, right? Because this is we can take gamma T1, say, gamma induced by T, plus gamma T2, 1 over 2. There's a convex combination, which is also a solution because the Kantorovich problem is a linear affine problem. And so we have some solution of the Kantorovich problem, which is not supported on the graph. And this is a contradiction to the twist condition, because the twist condition tells us that all solutions of the Kantorovich problem are supported on the graph. So this also implies uniqueness. So we need, in order to finish the argument, we need to close the duality gap. And we can do it in Polish spaces. So how we do it? If C is continuous, then we know that there is an optimal plane. That's the argue that it's enough for the existence of optimal plane, and the support of the optimal plane gamma, the measure gamma, is in a C-cyclical and monotone set. Then the theorem tells us that there exists a potential pair, phi C, of C-convex function, which satisfy this inequality on this cyclical and monotone set. Well, we can always assume that phi at some point x0 is 0, just add a constant and subtract the same constant from phi C to preserve this identity. So we know that phi C is the infimum of this definition, and C is bounded and continuous by assumption. We get that phi C is bounded and continuous. So the double transform, which is phi c is bounded and the continuous, and so also phi itself, which is the double transform of phi. So these two are defined. That's what we need to prove. Once they are defined, they must satisfy the equality because the maximum of the dual problem is bigger or equal than this integral, which is can be written as this integral of the double space x times y with respect to gamma, and this equal phi x plus phi c y is cxy, so this is just the Kantorovich value. So the dual value is bigger or equal to the Kantorovich value. But we know that it's smaller than equal to the Kantorovich value, right? Then we have equality. So this gives us the existence of solution and uniqueness under this twist condition for the Monge problem, but only on the assumption that the cos C is continuous and bounded. We can extend it to the case, to other cases, for example, this case, which is continuous but not bounded on Rn. So if the measure mu and nu has a finite second moment, and what we have to just to prove is that the potential phi and psi are integrable with respect to the measure mu and nu. So what does it mean? They are integrable. They are bounded by quadratic function. If they are bounded by quadratic function, then they are integrable with any measure which has a finite second moment. So we know that they are phi and psi are related by being this f is the Legendre transform of so x squared over 2 minus phi is the Legendre, y squared minus over 2 minus psi is the Legendre transform of x squared over 2 minus phi, and they are both convex. So they are, if they are convex, they are bounded from below by linear function. So if they are bounded from below by linear function, so the functions themselves are bounded from above by quadratic functions. And so we can justify the integrability on the space of finite second moment. Okay, so let's get some interesting conclusion from here. The first conclusion is polar factorization. What does it mean? In the space of P2, the space of measures on Rn with finite second moment, we claim that any mapping which maps mu to nu can be decomposed as a gradient of a convex function. That's what we saw now. So if we have a mapping T which push mu to nu, then T is the composition of a gradient of a convex function phi composed on a set or the mapping S such that S preserve the measure mu. So S is a mapping which preserve the measure mu, and any mapping any mapping which push mu to nu can be decomposed in this way. This is a direct result of the twist condition in the case of quadratic cos, right? Because we saw that in this case, well, maybe I'll move the slide before, remind you. this. Oh, here. So if H is just a quadratic function, in this case, then the gradient of H is just the identity. So we have that Y is X minus grad phi. So here's the identity, X minus grad phi is the gradient of 1/2 X squared minus phi, right? 1/2 X squared minus phi is a convex function, as we saw. So T is a gradient of a convex function, and this is the one which is optimal. The mapping which transports you to know in an optimal way. Any other mapping is just a composition of a mu preserving mapping with this optimal mapping T. And from here you can conclude some well-known theorem. For example, in linear algebra, you know that we can factorize any matrix by any matrix by a unitary matrix, rotation matrix U times positive semi-definite matrix S. So U, matrix U, orthogonal matrix is matrix which preserve the Lebesgue measure, and S being positive semi-definite is in fact a gradient of a convex function. Holmet's composition of vector fields also follows from here. If we have a vector field V in Rn, we can consider it as a perturbation of the identity. So take T of X equal X plus epsilon V of X. This is close to the identity transformation. So this is decomposed as we can make it a composition of a gradient of a function and which are also close to the identity with a function which preserve Lebesgue measure. So what is a gradient of a function close to the identity? We can write it as a gradient of 1/2 X squared plus some psi of X. Right? And which is just X plus, epsilon. X plus epsilon grad of psi of X. So this will be T. This will be grad phi of X, or the optimal one. And what will be S? S is a mapping which preserve the Lebesgue measure, so it is of the form S of X is X plus some epsilon time vector which is free divergence, right? If we take the Jacobian of such a mapping, the Jacobian will be of order epsilon square. So if we decompose these two functions one over the other, we get just a sum of the gradient of psi and phi. So the gradient phi acting on S is just X plus we'll call it Y. And then we substitute Y equal X plus epsilon phi, and we get that this is equal X plus epsilon gradient of psi plus phi. Okay, so any vector field V can be decomposed as a gradient and the free divergence classical result in analysis, and it follows for special case actually from this factorization theorem. Okay, let's Now let's see what happened if C is not continuous, just lower semi-continuous. What can we say in this case? If C is lower semi-continuous and bounded from below, again, it means that there exists a sequence, increasing sequence of continuous functions which converge to C. And we can look for the optimal solution of the Kantorovich problem for each of these segments CK. We know there exists one, and we know that the sequence gamma k are all tight. So there is a subsequence which converges to some measure gamma bar in pi. So if we take the limit of ck of mu nu, if we freeze one of the index k here, j, fix j, then you have this inequality because this is an increasing sequence, let's see, right? So we get that this limit is bigger or equal than this integral because Cj is continuous and the gamma k, we said, is a weak star convergence. So we have convergence, here convergence by duality to Cj d gamma. So by monotonicity, we guarantee that if we now take j to infinity, it converges to C, to the limit C, because it's monotone converge, and this is bigger than the optimal Kantorovich, right? Thus, we obtain that this limit is our semi-continuity of the Kantorovich value. And then we apply the machine of the duality and say, well, this is, you know that C mu nu is smaller or equal than this limit, and each of this is just equal to the solution of the dual problem. Here I cut out the definition of phi plus psi smaller or equal than ck. You should have ck, we don't see it. But if you replace this by phi plus psi smaller or equal than c, which is true because ck is smaller than c, right? So each pair of functions phi psi which satisfy this inequality also satisfy this inequality. So it's less equal to the supremum of our larger set, and this will be smaller than c. So we have all these inequalities turns into equality because we start and end with the same expression. So there is equality. So we see that the limit exists, so what can you say about the support of this optimal solution, optimal gamma? The supremum is for the dual problem is not necessarily obtained, right? Because if C is just lower semi-continuous, but we know there exists a sequence of phi and psi which satisfy this inequality, and their integral on the optimal gamma converges to 0. So at least we know that this sequence is converging gamma almost everywhere to 0. Thus, for a full gamma measure of the set gamma, this limit exists. So we have phi x plus psi y minus cxy equal, in fact equals 0 for gamma almost every point. So for any pairs x, I, y, I in gamma, we see that cyclical monotonicity exists by this condition. So again, also in this case, the cyclical monotonicity, there exists a cyclical monotone set which is in full measure of gamma, but it's not as, but it doesn't necessarily close, so we cannot say that is containing the support of gamma. Only so it cannot say that it is a closed set, but it is satisfy the duality condition for almost every point. Okay. Okay, I think I will not have time to finish this. Just make this important definition. We can use what we know so far to define this function, this called Wasserstein distance between two probability measures. This is the using the cost function x minus y to the power of p where p is bigger or equal to 1, and mu and nu are in the set of measures on Rn with a p bounded moment. And so we can prove now, and maybe tomorrow we do it, that, so we start doing it, that this is really a metric on a set of probability measures, P of P, right? By proving triangle inequality. Okay, I think I finish here.
Any questions? So the proof of stability, the proof you showed about the stability, it only works for continuous. The proof using the Hausdorff one, Vasquez, it only works for the continuous C, right?
The continuous
only continuous C. The proof you showed about the stability using the Vasquez theorem.
Yeah.
So the argument only works for continuous functions. No?
Yes. I saw. I made the assumption of continuous. Yeah.
But using lower semi-continuous approximation, you can prove
continuous. Then the question is if the support. I think it's true, but not to think about it. Okay. Yeah, I think it's true also for the lower semi-continuous function. That you can.
The argument about approximation by lower semi-continuous increasing functions should work.
Yeah.